Now we shall solve a non-homogeneous differential equation with constant coefficients. Here we have y double prime plus 4y prime plus 4y equals 8x minus 10. And as an addition, we will satisfy its complete solution with the given initial condition y equals 2, y prime equals 0 as x is equal to 0. The first step in solving a non-homogeneous differential equation with constant coefficients is that we shall find the complementary function of the homogeneous part of this equation, which is the left side of the equation. In finding the complementary function of the homogeneous part, we shall find the roots of the homogeneous part of the equation. So we have the homogeneous part y double prime plus 4y prime plus 4y equals 0. In order to find its roots, we can substitute m to the y, so we get m squared plus 4m plus 4 equals 0. Here, by factoring, we can get the roots. We can get the factor m plus 2 and another m plus 2. Thus, the factors are m1 is equal to negative 2. Same goes for m2, which is also negative 2. Using the factors, we can get now the complementary function. So we will get y is equal to c1 e to the negative 2x plus c2 x e to the negative 2x. Here we add a variable x in the complementary function because it is a repeating root. And the next step in finding the complete solution of a non-homogeneous differential equation is finding the particular integral of the right function of the equation. So the first thing in finding the particular integral is that we can find it separately or we can find it simultaneously, but for me it is easier to find it separately. So having the equation y double prime plus 4y prime plus 4y equals 8x, we can let y1 is equal to ax plus b. Then we shall substitute y1 to the equation. So we will get the 4a plus 4ax plus 4b equals 8x. Here, finding a and b, we can solve it simultaneously and getting 4a equals 8 and another equation 4a plus 4b equals 0. Now we can get directly a. A is 2, and by substituting a in this equation we can get b, which is negative 2. So substituting a and b to y1 is now 2x minus 2. And then another equation that we can form is y double prime plus 4y prime plus 4y equals negative 10. Here we can have a particular integral y2 again equals c, and by substituting the particular integral to the first equation, we will get 4c equals negative 10, and by solving this we shall get c is equal to negative 5 over 2. Now since we have c, we can now have y2 as negative 5 over 2, and we can get now the complete particular integral, which is y equals y1 plus y2. So by substituting the values we get earlier, we have 2x minus 2 minus 5 halves. By combining like terms, we will now have the complete particular integral 2x minus 9 halves. And now since we have the complementary function and the particular integral of both sides of the equation, we can now have the complete solution of the non-homogeneous differential equation, which is y is equal to c1 e to the negative 2x plus c2 x e to the negative 2x plus 2x minus 9 halves. But since we are given with the initial conditions that will satisfy the complementary function, I mean the complete solution, then by substituting y equals 2 when x is equal to 0 to this complete solution, we can solve for c1. So now by substituting y equals 2 when x equals 0 to the complete solution of the differential equation, we will have 2 equals c1 minus 9 halves. Here we can get c1 equals 13 over 2, and by substituting y prime is equal to 0 when x is equal to 0 to the complete solution, we will have 0 equals negative 2 c1 plus c2 plus 2. But by solving the equation and by substituting the value of c1 that we get, we can find c2 as negative 11. I mean positive 11. Since we now have c1 and c2, our complete general solution will now be y equals 13 over 2 e to the negative 2x plus 11 x e to the negative 2x plus 2x minus 9 halves. This time, we shall solve a Euler-Cauchy differential equation. Here we have x squared y double prime minus 6y equals 1 plus ln of x. In a Euler-Cauchy differential equation, we let x equals e to the z and z equals ln of x. The first step in solving a Euler-Cauchy differential equation is that we will convert the original equation into the equation that has a d operator. Thus we have d times d minus 1 times y minus 6y equals 1 plus z. By solving further the equation, we shall have d squared minus d minus 6 times y equals 1 plus z. Just like in the non-homogeneous differential equation, we will consider it as the homogeneous part, thus we will get its roots. And the same as getting another roots from a homogeneous part of the differential equation, we will have m squared minus m minus 6 equals 0. By factoring, we will get m minus 3 times m plus 2 equals 0. Thus, we have the roots m1 is 3 and m2 is negative 2. Thus, we will have a complementary function c1 e to the 3z plus c2 e to the negative 2z. After getting the complementary function, we will now try and get the particular integral of the right side of the equation. Thus, we will now again substitute y1 equals a for this first term of the equation. Thus, we have the equation negative 6a equals 1. Here we can find a is equal to negative 1/6. We can now find another particular integral for the second term. y2 is equal to bz plus c. We can now also get the equation negative b minus 6 bz minus 6c equal z. By solving this equation simultaneously, we will get b equals negative 1 over 6 and c equal to 1 over 36. Hence, we will now have y1 equals negative 1 over 6 and y2 is negative 1/6 z plus 1 over 36. Since we now have our complementary function and particular integral, we can now get our complete solution. Y is equal to c1 e to the 3z plus c2 e to the negative 2z minus 1/6 z minus 5/36. But since the variable of this equation is still not in the original variable x, we will still need to convert this and get y is equal to c1 x cubed plus c2 1/x squared minus 1/6 ln of x minus 5/36. We get this by using the substitution we have, which x equals e to the z and z equals ln of x. Now we shall solve another Euler-Cauchy differential equation. Again, the first step in solving a Euler-Cauchy differential equation is by converting the equation into the d operator equation and letting x equals e to the z and z is equal to ln of x. So we now have 2d times d minus 1 plus 5dy plus y equals 3e to the z plus 2. Evaluating further the equation, we will get 2d squared plus 3d plus 1 times y equals 3e to the z plus 2. Again, we will get a complementary function for this equation, and thus we must find its roots. So we now have 2m squared plus 3m plus 1 equals 0. By factoring, we will get 2m plus 1 times m plus 1 equals 0. So we will now have the roots m1 equals negative 1/2 and m2 is equal to negative 1. Thus, we will have the complementary function y equals c1 e to the negative 1/2 z plus c2 e to the negative z. The next step is finding the particular integral of the right side of the equation. So we will let y1 will be ae to the z. So we will get the equation 2ae to the z plus 3ae to the z plus ae to the z equals 3e to the z for the first term of the right hand part of the equation. Evaluating further the equation, we will get 6ae to z equals 3ez, and we will get a is equal to 1/2. And for the second term of the right part of the equation, we shall let y2 equal to b, and we will have b is equal to 2. So now we have the particular integral y1 is equal to 1/2 e to the z, and y2 is equal to 2. And since we already have the complementary function and the particular integral, we will now be able to get our complete solution, which is y is equal to c1 e to the negative 1/2 z plus c2 e to the negative z plus 1/2 e to the z plus 2. And since this is not still in the original variable x, we will need to convert it back to x. So we will get y is equal to c1 over square root of x plus c2 over x plus x over 2 plus 2.